Hi, I'm Mark Weitzman, and this is Quantum Field Theory, a student's perspective. Today's lesson is path integrals in quantum mechanics. It's chapter 6 in Srednicki's book, and it's probably this and the following couple of chapters are like the most important chapters in the book. So let's first start. There are three ways to do quantum mechanics. One is the Schrödinger way. This is usually referred to as wave mechanics. The second way is the Heisenberg way. This is matrix mechanics, also sometimes called operators. And then the third way is the path integral. Now, a long time ago when I was going to school, the path integral method was rarely taught in quantum mechanics classes, and sometimes not even in quantum field theory courses. But nowadays it's one of the primary methods of doing quantum field theory. And the story is that Richard Feynman was in a bar having a drink with a British or an Irish physicist, I can't remember. And he was talking physics, and he said something like, I need to understand what the classical action, for those of you who've had classical mechanics, it's usually called S, said, what's the role of the classical action in quantum mechanics? This was like in 1945 or something like that. And the guy said, I can't remember, but I know Dirac wrote a paper where he talked about that, so go read Dirac's paper. So Feynman read Dirac's paper, and Dirac basically said that the amplitude for something to go from x to x prime is analogous to e to the I s. I'm leaving out the h bars. Normally there would be like an h bar over here. As in this course we always have h bar equal to 1. And this action would be along the path that x moved to x prime. It's like classical. But the key thing that Dirac did was he didn't really do the computation, he just said it's analogous. And Feynman, after he read that, wanted to make it quantitative. And that's what he did, and he developed this path integral. And he thought he had discovered a new way of doing quantum mechanics, and he was like very happy. But later on he was disappointed because he realized, and everybody else realized, that the path integral method of doing quantum mechanics is equivalent to the Heisenberg and the Schrödinger. And you can show that these things are all equivalent. Now, one of the things that Feynman did, he wanted to do this because he was working on QED, quantum electrodynamics. Now it turns out you can do quantum electrodynamics in the what's called the canonical method without using path integrals. But for what's called non-abelian gauge theories like QCD, you really need the path integral to do it. Otherwise it's very, very hard, if not impossible. So the path integral ends up having a lot of uses. It's used in finance. It's called also the functional integral. And it's used in finance, it's used in chemistry, it's used in a lot of places. And there's a reference, a massive like 1,600 page reference by Kleinart. Everything you want to know about path integrals in there. But it's covered in just about all field theory books today and some quantum mechanics books. And a really good treatment is in this beginning quantum mechanics book by Shankar. He's got like one chapter where he introduces it and he shows how it's equivalent to the Schrödinger equation. And then he's got a whole like 70-page chapter at the end of the book where he talks about fermions and all kinds of things in path integrals. It's heavily used in condensed matter physics. And Feynman himself wrote one of the first books on, Feynman didn't write it, Hibbs really wrote it, but Feynman taught it, on quantum mechanics and path integrals. This was written in 1965, but it's still well worth reading. And nowadays, Weinberg in his book has a section on the path integral, and so does Weinberg, his very good book on quantum mechanics, and Ballantyne has a really good book on quantum mechanics. And just to give you one more reference if you want it, there are books like these. This is like not as massive as Kleinart, but if you want a more rigorous approach to path integrals, this kind of book will help you out. But remember, in theoretical physics especially, rigor often leads to rigor mortis. So we're not going to do anything with rigor in this book, in this course. So let me start by, before I do the math of the path integral, I want to go through an approach that Z does in his nutshell book. Where he gives the physical motivation for the path integral, and it's so obvious, and everybody who's watching these lectures, I'm sure you've had a course in quantum mechanics, you sort of know this, but it starts out where you have a double slit experiment. You have a source, a slit like this, then you have a screen, and the photons can go like this, or they can go like this. And let's say this is the observation point, and we say that the amplitude at O is equal to, the sum of the amplitudes that S goes to AI, which goes to O. This is this is 1 and this is 2. So this is, your normal double slit experiment, which is you sum this one and you sum this one. Now, to understand the Feynman path integral, what you do is you start putting more spaces here. So now you've got all these additional paths. And you sum them all. Now, this will be a constraint that it passes through, let's say this is X. It's got to pass through this. But if you put more screens, and you put more things like this, it's obvious after a while you're going to get every path possible. That's where the path integral approach comes from. You just pretend like these screens aren't here, and you end up having S, you're having O, and you calculate, the amplitude to go this way, the amplitude to go this way, the amplitude to go this way. You add them all up, that's the total amplitude. So that's the physical meaning of the Feynman path integral. Of course, mathematically, you got a lot of problems. What do you mean when you say sum them up? What's the measure? That's what a mathematician would say. What's the measure? Also, the question would be, what's the formula for the amplitude on a single path? So right now I'm going to go into the math, where we're going to calculate the actual path integral, and I will start that on the next video.